to Zeno. According to the realist view, by using the calculus, we basically change the concept of what instantaneous velocity is. What is the nature of this thing that we call instantaneous velocity? It's not that we just use the calculus to calculate the velocity. The calculus actually constitutes what instantaneous velocity is. Without the calculus, the notion seems not to make sense. We have a paradox, like in Zeno. We don't understand how can something move at a point of time. Does it answer to question? Okay, so that's an example. But there are other examples. I just don't want to get technical. So the issue is that if you are a realist, by looking at the calculus, you understand something about a physical quantity that we call instantaneous change. Okay? It's not just that you use it to calculate, you use it to understand, to interpret what is the nature of instantaneous change. Okay. Now, why the perception of mathematics changed? Big question and a difficult one. Now, in historical research, it's extremely difficult to point out with confidence why things happen the way they happen and why they change. It's difficult to give the causes of, if you ask historians, who will become nervous to say what is the cause of something. They will kind of say, you cannot talk, especially when you talk about things that happened a long time ago. And we have only the only information that we have is from archives, from things that remain, and sometimes very few things remain because they are lost or because I don't know destroyed, whatever. So it's difficult to say what were the causes of the change of perception. But it's possible to point out various factors that seem relevant for the change. So it's weaker than saying this is a cause. Saying that this seems relevant, that's what we are going to talk about today. And an historian mentioned, a number of factors. One of them is changing court structure of the Renaissance Europe enabled a mathematical practitioner to actually elevate the status. The university, they were kind of second-rate citizens in some sense. The natural philosophers were more important, but because there was also, so not everybody was at the university. Where was Leibniz? Yeah, it was a court. So for instance, Newton was in the university. Which university was Newton? Cambridge. So the issue is that he was more diverse. There were many people, including important philosophers, that were not in the university. So also mathematicians and other artisans so it turns out that in the court, it was easier for them to express themselves and to have more opportunities. So it wasn't like the university that had a very strict hierarchy of sciences, and that actually the mixed mathematical sciences like astronomy and optics came below natural science, below natural philosophy, below what Newton does in mechanics. So obviously the mathematician, it shows in some sense that mathematics is kind of less valued, less important. And changes, and these are social changes that were allowed people to, for whatever reason, times because the king or the prince or the ruler or the people who are reaching the court were interested in this. So as we see, for instance, that in the Renaissance, courts, important courts were interested in magic. So obviously, they were willing to sponsor and to have, people, natural philosophers who were interested in magic and alchemy, to sponsor them, to give them the means, to give them libraries, and to give them salary and so on, and they could work, translate books and so on. Now, in order to understand this, as I said, according to the mainstream scholastic Aristotelian view, Aristotle was very, very influential. Aristotelian philosophy, the Aristotelian philosophy and its evolution was very, very influenced, very, very important in the Middle Ages. And when we get to the Renaissance, this is still the ruling philosophy in the universities. And the natural philosophy was inherently non-mathematical. Mathematics was not at the center. But as I said, mathematics was not considered as the right tool to study the essences, the most important thing, the most general things about nature. So obviously, physics and mathematics, had a different status and position at the universities. So at the universities, mathematicians were more constrained. And the subject, also there was not as much connection as now. Now, as a physicist, a lot of the education, for instance, is mathematics. Actually, the same with economics. You study economics, and you study a lot of mathematical mathematics, probability, a lot of mathematical, actually some of the leading physicists, in the 20th century started as mathematicians. There were mathematicians that worked on programming physics. Like von Neumann, for instance, one of the greatest mathematicians. He was the one who formalized quantum mechanics. But he was main mathematician. He got the same, he got his Nobel Prize not for quantum mechanics, he got for game theory. Also mathematical. So everything he touched, became gold in a sense. But he did, he was mainly mathematician, but as a mathematician, it was much easier for him to work in physics because physics is very mathematical. In the 20th century, in the 19th century, but even more in the 20th century. But it wasn't the case. There was the methods of mechanics, for instance, and astronomy were different. Now astronomy is part of physics. It's like one of the fields. But it wasn't as connected as now. At least that's what historians believe. Okay. So the object of study of physics and mathematics were different. Physics was conceived in this neo-Aristotelian scholastic philosophy as studying the essences, nature of natural things, which are not separable from the things themselves. While mathematics was considered studying some attributes of things which could be conceived independently of the objects. So, we use mathematics to measure distance, for instance. But we can use them talk about distances without talking about objects. We use them in mathematics to talk about velocities, but we don't really need to talk about objects in order to talk about velocities as a mathematical entity. Something mathematical. We can abstract from the objects when we talk about mathematics. That's not the case in essences according to this philosophy. So in a sense, mathematics, yeah. So there were different methods, different conception of how they play in the understanding of nature, and therefore they were less connected. But the fact that the court, and there was this hierarchy, but the fact that the court were not constrained by the university hierarchy, okay, it's not that the court had the same standard as the university. What is this subject and what is that? It wasn't like that there is a, physics department and philosophy department and HPS100 department. The court, it's the court. The people are together and they can do, they're sponsored maybe sponsored by the same sponsor and talk to each other more easily and more flexible in that sense. So in order to bridge between physics and mathematics, early modern philosophers had to change not only mathematics and physics, but also the character of the classification at the universities. So the status and the classification of where is the place of mathematics and physics and astronomy and mechanics had to change. And in the new classification, those mixed mathematical sciences like astronomy became more prominent. Became like mechanics in a sense. And they gave rise to a science that integrated physics and mathematics better. And obviously it made mathematics more prominent. And mathematician. Nowadays, we don't distinguish so much between mathematician and physicist. Sometimes even mathematicians are more highly regarded. The physicists are considered sometimes, people will tell you that they work on practical things. But the mathematician really is more important. I'm not saying that it's true, but sometimes you will hear something like that. Another thing that stimulated the interest in mathematics was the discoveries of works of Archimedes, Platus, there was from Alexandria, these are kind of mathematicians, and even book that was a series of questions that was attributed mistakenly to Aristotle. If it's a book of Aristotle, obviously it's important, but it wasn't a book of Aristotle. And this also stimulated, this text stimulated interest and new interest and made the mathematician more bold, in their attitude and more confident. That one can use mathematics, for more than one use, up to that point. In general, as we shall see, that the Renaissance, part of the change in the Renaissance, especially in magic, was the discovery of books that were attributed to the ancient Greek or ancient Roman period. Okay. There also was a growing sense that mathematics is useful. More and more. The more mathematics developed, the more uses there were to it. And that's also contributed. And then there was the Jesuit pedagogy that the mathematics played an important role. And the Jesuits produced some very important philosophers and natural philosophers like Descartes. Descartes would be the next one that we studied. Descartes, for instance, was very important, in what we call science of physics, in natural philosophy. If you recall, Leibniz follows Descartes in his objection to Newton that there is no vacuum. And also Descartes is very important. It's one of the principles, philosophers in the theory of knowledge. So any course of theory of knowledge, epistemology, would have Descartes because his philosophy changed sense, well, some say even revolutionized or maybe, I mean, but his philosophy of knowledge was very, very important. Now, for him, mathematics was very important. And what kind of discovery in mathematics they got? Okay. Yeah, Cartesian geometry, I mean, so it's like, you know, the fact that you can study I mean, geometry in mathematical ways, which helps, I mean, instead, for instance, certain rules in certain ways, I mean, and looking at it, I mean, you open new ways that were not before. Okay. This is actually not the point, but it should be the conclusion. The conclusion is that by the end of the 17th century, when Newton presented his mechanics, mathematician exploitation. The book in which we have one of the chapter 3, Henry, that mathematician was regarded not as a mere underworker to the natural philosopher, but as one of the intellectual elite. Obviously, if you are part of the intellectual elite, I mean, your subject means that it's much more important. And to conclude this part, this quotation, I mean, maybe says more than anything, I mean, how mathematics became very important. So Galilei says philosophy, meaning nature, is written in that great book, which ever lies before our eyes, I mean the universe, but we cannot understand it if we do not first learn the language and grasp the symbol in which it was written. The book is written in mathematical language, and the symbols are triangles, circles, and other geometric figures, without whose help it is impossible to comprehend a single word of it, without which one wanders in vain through a dark labyrinth. Basically, I mean, in a sense, if you think about it, Galilei is a kind of neo-Pythagorean. He says that if you want to understand nature, you have to know mathematics. So this is the language. Like you cannot understand the play if you don't understand the language of the play. So if you want to understand nature, you have to learn mathematics, geometry. And that's a big change from the neo-Aristotelian. And that's actually, when you look at Newton, also Newton, when he defined time, he defined absolute time as also mathematical. It says time is blah, 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 mathematical, and so on. And the same for space. So one can say that Newton is also, in a sense, I mean, kind of neo-Pythagorean who has this view. And a lot of physicists, I mean, the 21st century has this view of it, that the world in some sense written in mathematical terms, and therefore, that's the reason why mathematics is so powerful in studying physics, and why we use it, I mean, to describe nature. Because basically nature, in some sense, is constituted by this language. So that's the right conceptual framework to understand nature. Okay. Let's have 10 minutes then and questions.